The discovery of an abnormally high concentration of the rare metal iridium at, or very close to, the KT boundary provides what has been recognized as one of those rare instantaneous geologic time markers that seem to be worldwide. This iridium anomaly, or spike, was first found by Walter Alvarez in the Cretaceous Tertiary stratigraphic sequence at Gubbio, Italy, in the 1970s. The spike has subsequently been detected at hundreds of localities in Denmark and elsewhere, both in rock outcrops on land and in core samples drilled from ocean floors. Iridium normally is a rare substance in rocks of Earth's crust, about 0.3 part per billion. At Gubbio, the iridium concentration is more than 20 times greater, 6.3 parts per billion, and it exceeds this concentration at other sites. Because the levels of iridium are higher in meteorites than on Earth, the Gubbio anomaly is thought to have an extraterrestrial explanation. If this is true, such extraterrestrial signatures will have a growing influence on the precision with which geologic time boundaries can be specified. The level of iridium in meteorites has been accepted as representing the average level throughout the solar system, and by extension, the universe. Accordingly, the iridium concentration at the KT boundary is widely attributed to a collision between Earth and a huge meteor or asteroid. The size of the object is estimated at about 10 kilometers, 6.2 miles, in diameter and 1 quadrillion metric tons in weight. The velocity at the time of impact is reckoned to have been several hundreds of thousands of kilometers per hour. The crater resulting from such a collision would be some 100 kilometers or more in diameter. Such an impact site, called an astrobleme, is the Chicxulub crater in the Yucatan Peninsula. A second, smaller impact site, which predates the Chicxulub site by about 2,000 to 5,000 years, appears at Boltysh in Ukraine. Its existence raises the possibility that the KT boundary event resulted from multiple extraterrestrial impacts. Although the amount of iridium dispersed worldwide was more consistent with the impact of a smaller object, such as a comet, the asteroid theory is widely accepted as the most probable explanation of the KT iridium anomaly. The asteroid theory does not, however, appear to account for all the paleontological data. An impact explosion of this kind would have ejected an enormous volume of terrestrial and asteroid material into the atmosphere, producing a cloud of dust and solid particles that would have encircled Earth and blocked out sunlight for many months, possibly years. The loss of sunlight could have eliminated photosynthesis and resulted in the death of plants and the subsequent extinction of herbivores, their predators, and scavengers. The KT mass extinctions, however, do not seem to be fully explained by this hypothesis. The stratigraphic record is most complete for extinctions of marine life, foraminifers, ammonites, coccolithophores, and the like. These apparently died out suddenly and simultaneously, and their extinction accords best with the asteroid theory. The fossil evidence of land dwellers, however, suggests a gradual rather than a sudden decline in dinosaurian diversity and possibly abundance. Alterations in terrestrial life seem to be best accounted for by environmental factors, such as the consequences of seafloor spreading and continental drift, resulting in continental fragmentation, climatic deterioration, increased seasonality, and perhaps changes in the distributions and compositions of terrestrial communities. But one phenomenon does not preclude another. It is entirely possible that a culmination of ordinary biological changes and some catastrophic events, including increased volcanic activity, took place around the end of the Cretaceous.